I don't have a new active assignment for you, but don't forget you have vocabulary to do over the weekend. Monday is Labor Day. Everybody's going to forget to do anything. So you have Tuesday to go, oh, that's right, I have homework, and turn it in on Tuesday night. All right. Okay, I'm going to be going through a PowerPoint. This PowerPoint is on Canvas on the Chapter 2 overview page. It may not have been updated, so if it looks a little different, just email me and I'll make sure to update it. Okay, so first thing, like I said, we're not really going to get into measuring stuff in this chapter, but coming up, I'm going to have you do conversions. And so I want you to have an idea of the things you're going to have to do. As you know, in the US, we use the English system. We're one of about 3 countries in the world that use this instead of the metric system. And England is not one of them. I'm not going to ask you to convert between English and the metric system, which is sometimes called SI. But what I would expect you to know is approximately how big is a centimeter or how much volume is a milliliter. And so this might help you to do that. When we get into chapter 3, I'll give you some kind of benchmarks to help you remember how big things are. As far as SI versus the metric system, technically they're slightly different. SI stands for the fancy French Système International. In the metric system, the base units are the ones that don't have any prefixes. So like meter versus kilometer or millimeter. So meter would be the base unit and gram would be the base unit. In the SI, some of those are a little bit different. So I think kilogram is the base unit instead of the gram. That doesn't matter to us. All we care about is getting from one to the other. So if you call it SI, if you call it metric, I don't care. All right, so what about getting from one place to the other? The bold ones are the ones that we use the most often, with the exception of deci. I don't know why that's bold, but we never use deci. So the bold ones are the ones that by the end of the semester, you're going to need to be familiar with those and be able to convert using those prefixes. For right now, I want you to focus on the ones that are 10 to the 3, 10 to the 6, 10 to the minus 3, 10 to the minus 6. So kilo, mega, milli, and micro. So you'll notice particularly down here, all of these exponents go 3, 6, 9, 12, 15, they all go by powers of 3. Now, you can memorize it however you want, as long as it helps you convert from one to another. So if it helps you to remember, oh, it's 1/10, let me divide by 10, sure, memorize that. If it helps you to remember what decimal place it is so that you can multiply by that, that's fine with me. For me, what I like about this notation with the scientific notation is the exponent tells me how far I'm moving the decimal. So if it's 10 to the minus 3, going from milli to no units, so from a milligram to a gram, I'm just scooching that decimal over 3 places. If it's micro, I'm moving it 6 places. So that's what's helpful to me. So by the time we get to exam 1, I'll probably have 1 or 2 questions that's like, if you have to weigh out 25 grams, but balance or 25 milligrams, and the balance only weighs in grams, what number of grams are you going to weigh out? So you'd have to convert 25 milligrams to grams. And we'll do some examples of that as we get closer. But if you're looking this weekend and you're like, it's so beautiful outside and the weather is perfect, and I really just don't want to go out there, I want to stay in my room where it's dark and I don't have to be exposed to such beauty, then this is what you can be studying while you're in your room. All right, some review. So we've looked at particulate views of matter. So each of these circles here is representing matter as particles. Now, of course, atoms don't have colors like this, so it's sort of an imagined view. But what phase of matter are all 4 of those? Exactly. They're a gas. The particles are separate, and we see the streaks coming out of them so that we know that they are going very fast. The first 2 represent elements. So the distinction I want to point out there is that in the first one, they're just atoms. In the second one, they're paired up. So as long as there's only one color in this case, or one element, it's still just called an element, even if there are molecules of them. Now, when they pair up, what do we call those kinds of molecules? We said these 7 over here fit into that category. Starting with a D. Diatomic, all right? So, and actually it's just the 6 over here, and then hydrogen, which is our misbehaving problem child, makes the 7th one. Okay, so when we get over to C, we have a dark gray center, and we have 3 light blue atoms around each of these. So each of these particles is the same. If each particle is the same, and it's not an element, right, because there's more than one color, then what are we representing here? A compound. So compounds, all the particles look the same. And so we can write a chemical formula for it. So if we knew black was carbon and blue was nitrogen or something, we could give a chemical formula for that. All right, and then in our last one, we've got lots of different kinds of particles, so it's a mixture. We had 2 different kinds of mixture, heterogeneous and homogeneous. The homogeneous we sometimes call a solution. Now, if there are only gases, then we don't have clumps of anything. And so this only has gases in it, and so this would be a solution. Now, if I have only liquids, it's possible for me to have heterogeneous. So like if you've ever had oil and vinegar salad dressing where it separates to the oil on top and vinegar on the bottom, there's 2 separate phases there, right? But in this case, with gases, they all just mix together. So if it's only gases, then it's going to be a solution. Now, that's different from if I have a cloud or smoke, because even though it's in the air, a cloud has little droplets of water, and smoke has little bits of solid particles, and that's what makes it hard to see through, okay? And so that's where we have to start thinking about, well, it's in the air, but can I tell if there's something else there by it being cloudy or opaque? And that tells us it would be heterogeneous. Okay, so those kinds of things also may show up on your quiz next Friday. Reminder, if we're looking at these particulate views, we have ways of distinguishing between something that is individual molecules that are next to each other and things that are individual atoms next to each other. So in both of these cases, we have particles that are solids, right? They're not spread out, and then they're not going all the way over to the edge. So that would be a solid. And in this case, each of those is a complete circle, where down at the bottom, the red circle is not quite complete. It's mushed up against the blue circle, right? In the blue circle, just a little bit of it's mushed together with that red. So that tells us that these 2 are bonded. But on the other side, these 2 just barely touch at that point. And so they're not bonded. So what we have is a pair, a pair, a pair, a pair, a pair, and a pair, okay? So these are molecules. So keeping in mind that they're molecules, would this be an ionic solid or a molecular solid? Go for the obvious. It's a molecular solid, okay? And it's making a repeating pattern. So it can have crystals in molecular solids like you would with sugar. Sugar can form crystals, but it's got molecules in it. But ions only form the crystals, whereas molecules could be crystalline like this, or they could just be just haphazard all over the place. Okay, so let's get to our atoms. And I want to kind of set the scene about when this was happening. So 1700s, we're getting into the age of enlightenment, the age of the scientific revolution. More people are interested in intellectual matters, and they're studying the natural world. Patrons in Europe are providing money for people to make discoveries and do different things. And what we're going to see is that as we have new discoveries, scientists are going to start obsessing on one aspect of it, and that's going to sort of drive science for a while. In the late 1700s, so right before what I'm about to talk about here, we are right after the Declaration of Independence. That would be 1776. So if you're from the US, right at the beginning of our country, some different scientists were using more modern machinery that allowed them to make more precise measurements, and they came up with some of these laws. So going into the early 1800s, these had been established. Probably the most important one on here is the conservation of mass. So I'll probably talk about that a little bit more than the others. That one's going to keep coming back throughout the semester. So whenever we say conservation, we mean that whatever it is we're conserving is the same before and after a reaction. So conservation of mass means that in a chemical reaction, the mass doesn't change. And as a consequence, the mass of all the reactants is equal to the mass of all the products. You put together all the reactants in your test tubes and vials and beakers and whatever, you weigh them. Afterwards, whatever you have should weigh the same thing. And that might seem obvious to us, but it wasn't so obvious at the time. And part of the reason it wasn't so obvious was that there wasn't a really good understanding of the air. We breathe it, we're in it all the time, but it wasn't obvious to people that it had mass or that it was matter. There were thoughts that it was a vacuum, that it was an ether, that it was spiritual, but the idea that it's made of the same kind of stuff that everything else was not something that was broadly understood. So Lavoisier and his wife slash girlfriend, I've heard her referred to as both, Marie, did a lot of work in the area of weighing things. That's where that new technology of being able to better measure things was important, and determining the mass of things before and after reactions. And so one of the things that they did is they took closed containers. So if you think of like an aquarium for fish, but instead of having an open top, sealing it, they would do chemical reactions inside this sealed container and weigh it before and after. And so from that, they could show that it weighed the same. So some people would say, I burned my log in the fireplace and the ashes don't weigh anywhere near what the log used to weigh. But they said, if you burned it inside this closed container, it would weigh the same. And so that tells us that the air around us has mass and is chemically doing something. So aside from that, he was able to establish that air supported fire, that you couldn't have a sustained fire in a closed place if you closed it off, because you would run out of oxygen. Okay, and so he sort of is credited with discovering oxygen, and he also established that animals can't live in an enclosed container for extended period, even with food and water, because there's something in the air that is supporting that life. But if you stick a plant in there, then that animal's fine. So the plant is giving off something they need. The animal needs something from the air. Fire needs something from the air. So air is chemically important and it has mass. So those kind of tied together with Lavoisier. And so he came up with the law of the conservation of mass. Now, when we say law, we mean that this is universally accepted. There aren't scientists that are naysayers about this. Nobody's saying, well, I don't think that's actually true. Think of the law of gravity. Nobody's going around saying, no, gravity's not a thing. And that there are no known exceptions. So once there are exceptions, then people would move that to more like a theory. Like, we think this is what's going on, but we have to kind of explain this other stuff. So with our laws, we're just saying this seems to be what happens. And we're not saying why it happens. We're just saying the mass is the same. So he didn't say why the mass was the same before and after. He just said, I've observed that every time there's a chemical reaction, the mass is the same before and after. Now, the next two might sound like they're contradicting each other, so I'm going to kind of go back and forth between them to illustrate the difference. So the law of definite proportions, sometimes called the law of constant proportions. So what we need to remember is proportion is like a ratio. Constant means it's the same. So this one says, if I have one compound, I'm only talking about one compound at a time. Every time I look at that compound, no matter how old it is, no matter where it came from, no matter how it was made, it is going to have the same ratio of elements. So if we think of water, whether that water is coming from my saliva, from the faucet, from a well, from the ocean, from the rain, there's always the same ratio of oxygen to hydrogen. Now, back in the 18 and 1700s, they couldn't count the atoms. They had no way of knowing about atoms. This before we discovered atoms. So they were looking at mass ratio. They'd say the mass of oxygen is this, the mass of the hydrogen is this. Or once they had electricity, they could look at the volumes and see that the volumes were proportional as well. So this one is dealing with only one compound at a time, and it's dealing with the ratio of those elements in the compound. So that's what the proportions is. The law of multiple proportions says that I can get different compounds from the same two elements, that every time I mix together these two elements, I'm not always going to get the same compound. So where this is coming from is if you think of, if I have flour and egg and butter and sugar, what am I making? Well, I might be making cookies. I might be making a loaf of bread. I might be making a lot of different things. I might be making a cracker. I might be making a mess. I'm probably making a mess. I can have lots of different things from those same ingredients, right? Okay, so we can have lots of different ratios that we use for our different elements, but they're going to have very different properties. So water is H2O. H2O2 also exists, okay? So this it's not saying that the law of definite proportions isn't true, because that one's just talking about one compound at a time. Law of multiple proportions says I can have a different ratio, but it will have different properties. How do I know it has different properties? Anybody know what this is, H2O2? So this is what we call hydrogen peroxide or peroxide. So you may have seen this in a brown bottle in a medicine cabinet. Sometimes you'll put it on cuts and it'll bubble and hurt a little bit. People used to use it as mouthwash to rinse out their mouths. Sometimes you might use it to clean clothes, to get as kind of like a mild bleach or something like that. So what we normally have in our medicine cabinet is about 3%. And you can do that. It's fine. It's also used in like a hairdresser's establishment if you're going to dye hair. So it takes the color out of hair, or it's used in swimming pools to kill off bacteria. And in that case, it's more like 30%. Now, if you get that on you, it turns your skin white and it hurts. I am not a swearing person. I might swear like a sailor if I get this on me. It really, really hurts. I've done that before. Okay, so 30% you don't want to be near. Okay. Water, I'll drink it, I'll shower in it, I'll swim in it, I'll take a bath in it. H2O2, I do not want to do those things with, right? So the point of the law of multiple proportions is that if I change the ratios, I've got a different compound, okay? There might be different ratios, but it's not the same thing. So some other examples. Carbon monoxide and carbon dioxide are different things. So we breathe out carbon dioxide, which means that it's in the air, so we breathe it in. If you've ever seen somebody have rescue breaths during CPR, like obviously some carbon dioxide is coming out of the mouth of the person giving the rescue breaths. So a little bit of carbon dioxide isn't going to hurt, right? Carbon monoxide, we have detectors for, because even in very small amounts, that can kill you. Okay, so very similar, but different ratios means it's a different compound, different properties. Now, if we look at nitrogen and oxygen is really the element that does a lot of this multiple proportion things. We have 6 different compounds listed here. So these are components of pollution. This one's a brown one that can make the air look orange or brown, like during a forest fire. If you've seen like a haze around a forest fire that's kind of orangey or rust colored, that's this. But this compound, which looks similar, is laughing gas. It's an anesthesia that's used for like if they extract a tooth or do a root canal or something, they might give you this as your anesthesia. So these are very different compounds when I change what those ratios are. So that's kind of the point of that. So I might ask you, give you an example and say, which of these laws am I illustrating? Or I might say, here's a law, which of these 4 choices is an example? Anticipate that being how I would ask about it. All right, so we get to the early 1800s and we get Dalton.